We're now ready to begin the fourth video of this introduction to plate tectonics. In this fourth video, I'll cover earthquakes, magnetics, and hotspots. The learning goals in this case are to understand what is the connection between earthquakes and plate boundaries and plate tectonics. Furthermore, the orientation of Earth's magnetic field when locked into rocks is used to determine the prior locations of the plates, and the role of hotspots in recording both plate motions and determining a coordinate system for plate tectonics. So, on earthquakes, we need to know something about the location of earthquakes and how the rock moves at the location of the earthquake, which is the focal mechanism. On the magnetic side, we'll talk about the record of magnetics from the continents, and these are polar wander curves, and the evidence from the marine oceanic rocks, which are the marine magnetic anomalies, and they show the history of spreading. So let's talk about earthquakes and the mechanisms of earthquakes. First of all, it's a pretty simple idea. Earthquakes occur, the rock breaks, elastic waves are sent out around the world. These seismic waves travel the entire distance from any point on the Earth's surface. A distribution of seismic stations around the world record the arrival of these elastic waves from earthquakes. And the location of the earthquake is determined by triangulation. If you know when the waves arrive at different locations, you can work backward and figure out where the wave originated. At each of the earthquake recording stations, you can determine how the ground moved when the seismic wave arrived. Did the ground move up or did the ground move down to begin with? And whether it moves this way or that way gives evidence on how the rock moved at the location of the fault at the earthquake epicenter. So by determining the motion of the waves at the seismic stations around the world, we determine the way the rock moved in the earthquake. And this way the earth moved at the earthquake location is the focal mechanism. So we turn back to our map of the entire globe showing all the plates and plate boundaries. The beautiful thing is the plates and the plate boundaries are defined by the locations of the earthquakes. Notice one-to-one correlation between where the earthquakes occur and where most of the where the boundaries are. So most of the earthquakes occur on plate boundaries. You can watch the spreading centers around the world. It's a thin line of earthquakes following the active spreading. In subduction zones, you see broader trends of earthquakes, and let's see, if you look along the South American coastline, you can see the trend of earthquakes shallow at the coastline, deeper as you go inland. Again, this is the Wadati-Benioff zone trend of deeper earthquakes, deep following the trend of the subducting slab. The boundaries are well defined and fairly narrow in many cases. In some cases, moving across Asia and Europe, you see a very wide band because this is a continent-continent collision area, and a broad band of deformation of the rock on the boundaries. So there are three types of faults, and each of these faults have a specific signature in their earthquakes. There's strike-slip faults, which are vertical or near vertical, and the motion is side by side. It's also known as a transform fault, and they're the kind of faults motion that you have on transform boundaries. So here's a photograph, not a photograph, here's an image of a transform fault, and you see the side-by-side motion of the two plates, brittle failure in the rock at the near surface, ductile behavior below that. So the motion is entirely horizontal in a transform or strike-slip fault. Now, thrust faults involve shortening of the land, and one block of rock is thrust up over another block of rock. And so here's the picture. So if you are shortening the land, as in a convergent zone, you get thrust fault earthquakes. Ductile flow again at depth, and brittle failure in an earthquake near the surface. So the motion is partially horizontal, partially vertical. Finally, there are normal faults. And normal faults occur in situations in which there is a pulling apart of rock masses. So if you stretch it out, the rock breaks and slides against itself, as illustrated here. Beneath the brittle layer, there's the ductile behavior where spreading is occurring. So again, it's partly horizontal and partly vertical motion on normal faults. So faults, three types of faults, three types of plate boundaries. And the beautiful thing, this was part of the evidence that supported plate tectonics in the 1960s, is the motion of faults as determined by focal mechanisms on seismic records match the expectations of movements of plate boundaries. So normal faults, that's a pull apart faulting. Those are the kind of earthquakes you see at spreading centers. Strike slip motion, that's the transform faults. The strike-slip earthquakes occur at transform boundaries like the San Andreas Fault, the Anatolia Fault, and all those offset transform boundaries of offsetting segments of seafloor spreading. Finally, thrust faulting is the kind of faulting that dominates in subduction zones, where there's convergence of the plates. That turns our attention away from seismology and into magnetics. So the Earth has a magnetic field. We know that. Every Boy Scout or Girl Scout has gone out and used a compass to orient themselves. The Earth's magnetic field is produced by a dynamo process that originates by circulation of molten conducting fluid in the Earth's core. The iron mixture in the core under convective motion generates magnetic field. This magnetic field is dominantly dipole, which is the bar magnet kind of field, and it's located essentially at the center of the Earth. This field, on average, lines up with the axes of the Earth. That's why compass needles point almost to the north, and we say compass points to the north because there's a lineup of the magnetic field with the rotational axis. Currently, however, Earth's magnetic field is tilted by 11.5 degrees from the rotational axis of the Earth, and I'll talk about that in more detail later. Now, the field the field varies in direction from the pole to the equator. At the equator, the Earth's magnetic field is horizontal. At the poles, the Earth's magnetic field is almost vertical. And that's an important thing because, number one, compasses don't work very well at the poles. You know, a compass needle standing on the pole is trying to point either straight down or straight up, whereas a compass needle at the equator is aligned with a magnetic field that is horizontal. So in fact, if you have a compass free to turn on a vertical axis, you can use a compass to determine how far north or south you are. The inclination of the Earth's magnetic field is a measure of distance from the magnetic pole. Finally, the Earth's magnetic field has a tendency to flip directions completely. Currently, compasses point north, but if you had been around 800,000 years ago, compasses would have pointed towards the south. Let's look in detail at some of these properties that I just said in words. So there's the Earth. There's the spin axis with north at the top and south at the bottom. There is a magnet, a dipole magnet, oriented at an angle of about 11 degrees right at the Earth's center. That magnet then produces a magnetic field as illustrated here, where I've color-coded it with compass needles pointing in yellow and pointing out in blue. So if you follow how a compass would orient itself at various points, you see as if we started deep inside the Earth, it'd be pointing up and out. As you come to the Earth's surface in the southern hemisphere, it's pointing up and towards the north. As you move around towards the magnetic equator, it's pointing horizontal, tangent to the Earth's surface. And then as you enter the northern hemisphere, the magnetic lines of force, or the direction compass needles point, begin to go into the Earth as well as point towards the North Pole. Now notice that at the south magnetic pole, the magnetic lines are pointing straight out of the Earth, and at the equator, magnetic field lines are tangential to the Earth's surface or horizontal, and at the North Pole, they are oriented vertical, pointing into the Earth. Now, the Earth's field is currently at this angle of 11 degrees from the spin axis, but if you'd gone back at various points in time, you would have found it oscillating around near the spin axis of the Earth, but on average not exactly aligned with the Earth's axis, just pointed 10 degrees this way, 10 degrees that way, and then sometimes flipped around. See here it's with the South Pole at the north, and here it's North Pole at the south. So this represents the flip of the field. Last one was 780,000 years ago. Now, that's what the Earth's magnetic field does. Let's talk about what rocks do and how rocks can give us a record of magnetic field in the past. Many crustal rocks contain minerals that are magnetic. And so here's a box representing a rock, and little red arrows represent magnetic minerals. Now, if there were no magnetic fields to align them, these magnetic minerals would just point in random directions. But since there is a magnetic field of the Earth, the magnetic minerals within the rock, when the rock forms, tends to align themselves parallel to the Earth's magnetic field, as shown here. So there is a magnetic moment, a magnetic field associated with the rock, which exists even if there were no external field, the Earth's magnetic field. So the rock can be a magnet on its own. It's a magnet because these minerals, which are a very small fraction of the total bulk of the rock, can be aligned parallel to some external magnetic field. So there's a picture showing magnetic field lines with that one rock. So the rock forms, it's permanently magnetized in the direction of the Earth's field. It maintains that record of magnetization on some cases for geologic time. So why is that important? Let's look at a field called paleomagnetism, and let's again look at the Earth's magnetic field at the equator, which is horizontal. If a rock, and then at the magnetic pole, the magnetic field is pointing straight down. In between the magnetic field lines at the Earth's surface, point increasingly downwards as you move from the equator towards the pole. If a rock is formed on the equator, it will have a magnetization that is horizontal. Now, if that rock were transported by drifting continents to somewhere in the northern hemisphere, you see the rock still has a horizontal magnetization, but it is now in a location where the magnetic field is dipping strongly. So there's two possibilities. Possibility one is the rock actually moved from where it formed to where it is now. And the other possibility is that Earth's magnetic field changed, that when the rock formed, the Earth's pole was somewhere way out to the side there. See, so here's where the pole is now, but if in the past the pole were over here, then the rock didn't have to move. It could have just stayed in place, formed magnetization parallel to the Earth's magnetic field, and then if the field changed, that would then generate a difference between the rock's magnetization and the current magnetic field. So, what is continental paleomagnetism? What you do is you go out and you examine the magnetization of rocks of different age from all the continents. So you gain a record of how the magnetic field changed over time. You determine the direction to the magnetic pole and the distance to the pole in each of these rocks at each point in time. You can plot these data in two different ways. You can plot it as if the continent stayed still and it was the pole that moved, or you could plot it as the pole stayed where it is and the continents moved relative to the pole. Let's look at these two ways of representing the data, and I'll give you the name now. It's called the apparent polar wander path. And it's apparent because we don't know whether it's the pole that moved or the continent when we first take these data. Now, South America is sitting here. Rocks have been collected of various age on South America. The rocks of various age show a different location of the magnetic pole relative to South America. 500 million years ago, the red dot there represents where the pole was for South America. So South America had the magnetic pole off to the northwest. Now, that pole moved through time until currently the pole is appropriately at the South Pole. Let me go back and do that again. So this apparent polar wander path represents a path that the magnetic pole took relative to South America through time. So one interpretation at this point is that South America stayed right where it was and Earth's magnetic field kept changing over time. This path linking all the different ages and the location of the poles is called the apparent polar wander curve. Now, the alternative way of plotting this data is to assume that the pole didn't move and it was the continent that moved. So 500 million years ago, South America sat in a position like this relative to the South Pole. Then, taking those paleomagnetic data, you would project that over time, South America moved as illustrated here. It moved from being on the far side of the pole to the other side of the pole. Shall I do that again? So here, South Pole is to the northwest of South America, but as South America drifted along, it drifted by the South Pole and then off to the north, relative to a fixed magnetic pole. So, two representations. Was it the continent that moved or the pole that moved? If a pole moved, then the apparent polar wander paths should be the same for every continent, because it's one pole and all continents should have rocks that point to the same pole. However, if the pole stayed fixed and it was the continents that moved, then apparent polar wander curves for North America, South America, Asia, and Africa should be different if those continents moved in different directions through geologic time. This graph here shows that, in fact, this is the case, that the apparent polar wander curves for Europe are different than the apparent polar wander curves for America. One in open circles, the other in dark circles. So, in fact, this paleomagnetic evidence showed that continents moved and magnetic poles stayed relatively fixed along the axis of rotation. So there it is. Different apparent polar wander curves for different continents imply the continents must move, not the poles. And we can use the apparent polar wander curves then to reconstruct past locations of the continents. Now let's turn to the marine magnetic anomalies, the marine magnetic record, distinct from the continental magnetic record. Okay, so here we have again cross-section through the Earth. There's a representation of Earth's magnetic field dipping into the Earth. Ridge, not showing up as a ridge in this diagram, but this is where new volcanic material comes up to the Earth's surface. It comes to the surface, it cools off. That 5 kilometers of basalt at the mid-ocean ridge spreading center cools and takes on the magnetic orientation of Earth's magnetic field at the point and time that the basalt cooled. That basalt is transported away from the ridge through seafloor spreading, and sometime later Earth's magnetic field may have reversed direction, shown white here pointing up out of the Earth. New basalt flowing up at the mid-ocean spreading ridge now will cool and take on an orientation in the opposite direction that from the previous block. Now both of those blocks continue to be transported away from the ridge by the passive transport associated with mid-ocean ridge spreading. And if the Earth's magnetic field flips again, we have yet another block and another orientation of magnetic field. This process can continue on, generating essentially stripes of magnetized material. One stripe has the one orientation, the other stripe has the reverse orientation. So these stripes across the ocean floor record, just as a tape recorder records the magnetic orientation at the time that the tape came out, the volcanoes erupted, the magma cooled and solidified a magnetization parallel to the Earth's magnetic field. So in the 60s, these magnetizations were first recognized. Here's a classic paper from 1966 with just a little bit of data south of Iceland across the mid-Atlantic spreading center, and you see stripes of black and white representing normal and reverse polarization of the rock. These stripes then looked symmetric about the ridge and gave evidence for a seafloor spreading process. Since 1966, many more oceanic surveys have been conducted, and we know a lot more about where the anomalies are. Here's superimposing on that a more recent diagram identifying magnetic anomalies by lines. So you notice the lines continue from the identified anomalies in that Hertzler paper out in all directions. So here's a map showing not as black and white, but as simply lines drawn through the maximum of the anomalies. And you'll notice that there's a pattern. They're numbered on either side of the seafloor spreading. And associated with this is a chronology of when the Earth's magnetic field reversed. Across the bottom, you see age versus anomaly number. And for instance, you can look on either side of the mid-ocean ridge spreading center south of Iceland. There's the lines identified as anomaly 4. Anomaly 4 on this horizontal scale is as shown there. You project across the diagram, and anomaly 4 was made at about 7 million years ago. So there are all the other anomalies, each of which has an associated age. We can, in fact, date the seafloor from the anomalies without even having to go and drill and get samples. Now, there are some places, I've circled one here, where seafloor expeditions, drilling expeditions have gone and drilled and taken samples from the seafloor. But those are very, very few places compared to the many other places where the magnetic anomalies can be recognized simply by dragging a magnetometer across the ocean. Having dragged the magnetometer around, identified anomalies, it's possible to date all of the ocean floor. And here's a summary of our knowledge of the age of the ocean floor. The warm colors are young, the colder colors are old. And on this scale, you go from 0 back to approximately 200 million years. Notice on this diagram that the oldest parts of the ocean are in the western, far western Pacific, where ages are up close to 200 million years old. Notice in this diagram that a slow spreading center like the North Mid-Atlantic Ridge, the red colors stay close to the ridge because it's spreading slowly, whereas for the East Pacific rise with a much higher spreading rate, the red colors extend farther out from the ridge. So the beauty of the marine magnetic anomalies is an ability to reconstruct and determine age of the seafloor, and determine the age of the seafloor then allows us to reconstruct the process of seafloor spreading. Finally, in this talk, I want to talk about hotspots. Well, there are several dozen volcanoes around the world that appear fixed relative to the plates that are riding across them. And these volcanoes seem to be fixed with each other as well as with relative to the plates. It implies that there may be a deep-seated source of magma, perhaps the core mantle boundary, that is feeding these volcanoes. And if that's true, then it helps define a coordinate system independent of the plates to define how plates are moving on Earth's surface. Interesting thing about these volcanoes is they have distinct chemistry. They're basaltic, but they're not the same mantle source as the mantle that is melting to form the spreading center basalt. We call these mid-ocean ridge, ocean island basalts, hotspot basalts, OIBs for ocean island basalt. The idea of a hotspot is this: we have a conduit from deep in the mantle coming up underneath the plate. A blob of material comes through and forms a volcano. The plate moves, carries the volcano off, the volcano becomes extinct. A new blob of material comes up the conduit, forms a new volcano. And this volcano again gets carried away by the plate motion and allowing a new volcano to form. So we have a series of volcanoes, the youngest sitting right over the hot spot, older volcano moving away from the hot spot. The oldest volcanoes are farthest from the hot spot. An example of this in the Pacific, one of the best examples, is Hawaii. And you see Hawaii down there. You see a trend of volcanoes across the Pacific. The current plate direction of the Pacific plate is exactly parallel to the trend of these volcanoes in the seafloor. The age of the youngest volcano is 0. We're actively erupting on the big island of Hawaii. As you move back across the exposed Hawaiian Islands, when you're back on Oahu, the age of the rock is about 2 million years. As you go out to the oldest of the Hawaiian Islands, it's 5 million years. As you extend across to the submerged seamounds to the northwest, they're 12 million years old. At Midway Island, they're 27 million years old. Farther out, it's 43 million years old. Now, there seems to have been a different direction of motion, perhaps, prior to about 50 million years ago. And the volcanoes continue to get older as you move along that trend. So there's a progression of ages away from Hawaii, recording the movement of the plate across a hot spot. I said there are a couple dozen hot spots around the world. Here's a map showing the location of places that have been identified as hot spots. Some of the best known examples: Hawaii, Yellowstone, Iceland, Reunion Island, Bermuda, Galapagos. These are all well-known ocean islands that are probably hot spots. Hotspot tracks, that track of progressively older volcanoes, was one of the early lines of evidence that supported this newly emerging idea of plate tectonics. We use the hotspots to help define the fixed coordinate system beneath the plates. Hotspots, with their unique geochemical signature, tell us more about how heterogeneous and how differentiated the Earth's mantle is. Hotspots themselves account for about 10% of all the heat coming out of the Earth. Most of the heat comes out through the mid-ocean ridge spreading centers, but 10% of it is associated with hotspots. Finally, there's an idea that hotspots may have been more numerous 100 million years or more ago, and this is an interesting area of speculation. So all of this brings to an end this series of talks that give you the bare minimum knowledge of plate tectonics. I have to give credit to a variety of textbooks from which I've lifted illustrations. I have also pulled out illustrations from various research publications, from Google Earth, and from Wikipedia Commons.